It's a great pleasure to have Glenn Shafer, one of the greatest authorities on the foundation of probability and a pioneer in Bayesian statistics, talk about some very interesting stuff, the language of betting as a strategy for scientific communication.
Well, thank you, Doron. You mentioned Bayesian, so I should say this talk is not Bayesian. This talk is really about conventional statistical methods, but it's kind of about statistics. It's about a way of interpreting conventional statistical methods that they might be communicated better. Let's see how this is going to work. Yeah. Here's there's been a lot of publication. I don't know, I may have chosen the wrong audience for this talk, or the wrong talk for this audience. I assume that most of you have heard of the notion of a significance test in statistics, or a p-value. So those are the ideas I want to talk about. They're ideas that are taught. There's probably 1 million people every year in the United States that are taught in classrooms the theory of statistical significance testing. I say that because, there are 20 million college students in the U.S., and that means there must be about 4 or 5 million freshmen, and at least a fourth of them, either in high school already or in college, are learning about significance.
They're learning, but they're not getting it.
And so, but it turns out that nobody gets it. So one of the most discouraging things in recent years is, because of so much misuse of p-values, some people had the bright idea of giving quizzes to the people who teach and use p-values. Not just the ordinary student, but the ones who teach it and use it. And it turns out they can't answer questions correctly. So these are just two survey instruments that have been used. They asked their questions, you got a significance test, p-value 1% or 5%. Which of the following statements are true? Well, all the statements are false. But the majority of teachers of statistics, the majority of medical researchers that use statistics, majority of social scientists that use statistics do not answer all these questions correctly. So there's something, basically, it's too hard. It's too hard. Let's see, go back a little bit. So my theme here is that the conventional vocabulary is too complicated, and that we could do better using a language of betting. So my idea is that probability was always about betting, and what we've done is we've tried to make it sound more objective by not talking about the betting. But if we talk about the betting, then the sort of uncertainties involved will be clearer, and there's less, we'll fall into mistakes less easily. That's my hope. And then point 2 and 3, I will talk more about. I'll make it a little more in depth if I get there, but point 1 is the one that's really on my mind, even though it's very, very simple. So I may spend the hour on point 1, but if I have time, I'll get to point 2, which is more about what's in the book I've written. I'm a co-author. We are publishing our second book on game-theoretic probability. It will appear in May of...
So it's a new book, it's not a new edition.
It's a new book. We originally thought it would be a new edition, but we completely rewrote it. There's hardly anything from the first book. It has new ideas, and even what was in the first edition has been completely redone. So it's a new book, Game-Theoretic Foundations for Probability and Finance. On the back of it, we have some blurbs from some well-known people. Karatzis, does mathematical finance at Columbia, has given us a nice blurb. And a friend of mine, Peter Grunewald, at University of Leiden, has a nice blurb. We got a nice picture on it of card players. This is a painting from 1520 by Lucas van Leyden. It has different interpretations, but this is probably Charles V, and this is the Cardinal Wolsey. So they are, big things going on there. So I'll get to some of the things in that book, but my first point about communicating statistical results using the language of betting is something that's so elementary that we didn't even put in the book. And I'm now thinking maybe we should have put something really simple. So it's about what are the conventional concepts that I'm going to talk about. The conventional concepts are significance test, and you may remember the significance level, which is the probability that the test rejects the probability distribution. P here is a probability distribution. We're testing the probability distribution. What is the probability, if it's true, that we reject it? The power is the probability rejected if some other distribution is the true one. The p-value is the probability that a test statistic is bigger than the value we actually observed. So when this happens, we say, oh, a rare event has happened. We can reject this probability distribution because it's saying a rare event has happened. There's another concept which is not quite so elementary as these. It doesn't always appear in the elementary expositions. It's the likelihood ratio. That is, given the observation, how much more likely is it under Q than under P? Where P is what we're testing, and Q is the alternative hypothesis. This one is not as widely used quite, but it's going to play a role in what I have to say.
P and Q are probability distributions?
Yes. Yes. P and Q are probability distributions, and we are testing P. Oh, excuse me. We're testing P, and maybe underlying our test is the idea that maybe P is wrong and Q is right. But the point is, P is the one that is the straw man, the one we're testing. So as I say, this p-value idea, people don't answer questions correctly about it. Power is very important, but generally in the elementary teaching it's not talked about. And in most papers that are published in social science or in the business school where I teach, you don't see any mention of power. That's too hard. Here what I'm going to talk about is how we could give these things betting interpretations. So these are the conventional explanations. And if we think in terms of betting, we can give them a different explanation. I'll need to explain to you what a betting score is. A betting score, I'll go into it in detail. A betting score is how much you multiply your money by when you're betting against the probability distribution. And it turns out that you can bet so that this is actually your betting score. And it turns out the significance level is the inverse of the betting score for a certain bet. And I want to in my story here, I think we can better understand the point of power if we talk about betting. And we can understand also why p-values are really cheating. It becomes very clear why they're cheating.
When you say test, you're talking about an algorithm, a specific... You didn't define what you meant by test. It's an algorithm.
I'm going to tell. So now I'm going to... that chart was kind of referring to what people in the standard textbooks mean by test. But now I'll tell what I mean by test. Because I have a different way of testing. My way of testing a probability distribution is to bet against it. So I interpret the probability distribution as offering me bets. And I want to choose a bet. And my goal will be to multiply my money. And if I multiply my money by a lot, I'll say that's the best evidence I can have it, but this probability distribution is wrong. This probability distribution set these odds. I bet by those odds, and I made a lot of money. That shouldn't have happened if the probability distribution was a good probability distribution. I've proven it's bad. Now, we all understand that I could have been lucky. I could have been lucky. We all understand that. That's why I think this is a good language to use, because the uncertainty involved is on the surface. You all understand that I could be lucky. Just because I multiplied my money by 1 million, it could have been a fluke. But there's no better evidence again than that I multiplied my money by 1 million. Now, there's one detail. We've got to talk about what I've got to do to be convincing. I've got to multiply the money I risk. Now, if you talk about people that make a lot of money gambling or let's say in the stock market, the people who come out billionaires from the stock market are actually not risking just their own money. They can do that because they're risking somebody else's money and they get a cut if they win. If they lost it, it wasn't all their money they were losing. So that's how people can win $1 billion in the stock market. It's because it wasn't all. They were risking somebody else's money. I'm talking about risking your own money, or my own money. I want to take the money I risk and multiply it by a large amount. So the probability distribution so the idea is I will, I don't know what that's doing there. So the probability distribution is claiming to describe this phenomenon Y, and Y is going to have some particular outcome, little y. This is a notation that was invented in 1900 by Andrei Markov and is often used in probability teaching. How many of you have seen this convention? Big Y and little y? How many have not seen it? Okay, so it's very common in statistics books and probability textbooks. So big Y is the random variable. It's not been decided what it is yet. Little y is the value you see. So I am going to, this probability distribution for capital Y, I will say, well, if you think P is the probability distribution for capital Y, then you should let me buy any payoff, any function of Y, any real valued function of Y, any payoff, for its expected value. And what I'm going to do is I'm going to buy a non-negative payoff with expected value 1. And since it's non-negative, I only risk what I paid, the $1. So the betting score will be how much I multiply my $1 by. In other words, it's f of y. So very simple. You give me the probability distribution, I choose a non-random, I choose a non-negative variable, a non-negative function of the outcome that has expected value 1, and that's my payoff. And if that comes out 1 million, I only paid $1, I got 1 million, your probability distribution is not very good. That's the idea. But as I said, the possibility I was barely lucky remains in view, and I think my line is there's no better way to communicate the remaining uncertainty. Now, you've already read what I wrote in red. There's no Bayesian reasoning here. Bayesian reasoning has to do, and utility theory and all that economic stuff has to do with when you're risking something that's meaningful to you. I'm just going to risk $1. I don't care. I'm a rich guy. I don't care about $1. And if $1 is too big an amount of money for you to throw away, then just risk 1 penny. It doesn't matter. The point is how much you multiply it by. This is not about decision theory or utility theory or anything like that. Okay, so now I wanted to say this likelihood ratio, this is a statistician's name for it. That name was invented by a statistician named R.A. Fisher in the 1920s. And it's been used on all the statistics literature in the 100 years since then. The likelihood ratio is the ratio of the probability that the ratio of Q's probability for the observation I actually saw over P's probability. And the likelihood ratio is a betting score because well, what is it? What do I mean? If I buy an F, a non-negative f with expected value 1, it will turn out to be a likelihood ratio. Because the statement that its expected value is equal to 1 can be written like this. If I sum over all the possible values times their probability, that's 1. Well, remember, a probability distribution is just something whose probabilities add up to 1. So f times p is also a probability distribution. We call it q. F is equal to q over p. So the bet I choose, whatever bet I choose, it defines an alternative probability distribution. Now, this seems like a... So here's, I should give this talk to the stat department because, well, partly they might be more interested, I guess, but partly they might be able to tell me who did this before. This must be ordinary. It's very simple. This way of testing a probability distribution, people must have written about it. I can't find any references. I can't find my predecessors about this. It is, I mean, I mentioned that book that is coming out by Vovk and myself. We wrote a previous version in 2001, and these ideas were embedded in that. But here I've boiled it down to something very simple.
Maybe it's too simple for them.
Pardon?
Maybe it's too simple.
Too simple.
You'd like to make it complicated.
What do you mean, whether it's been done before or not? The betting interpretation or the likelihood? I mean, obviously the likelihood ratio is used.
The likelihood ratio is used, but this betting interpretation of it, and the idea of testing a hypothesis by trying to multiply the money you risk.
And the Dutch book and what happens in the
It's not Dutch book. There's nothing about Dutch book here.
Yeah.
No. I'm not, because I'm just risking a negligible amount of money. The point is, the way I test is trying to multiply my money. And when I do that, I have defined an alternative distribution. And the amount by which I multiply my money is the likelihood ratio with that alternative distribution. I've never seen anybody, I don't have any references. I feel like this is so simple to claim that my colleague and I invented it seems ridiculous. So I'm thinking, well, who said this before? And I can't.
So it's a true breakthrough. It was so simple. I overlooked.
Maybe.
Many great
Maybe somebody will tell me. Okay. I mean, there are things like this. Well, here's a detail. This is something that people have written about. There's a classical, I think the classical reference for this idea is Leo Breiman's paper in the Berkeley Symposium in 1961 about optimal betting in favorable games. So the point here is that if you did think that Q was the alternative distribution, if you thought Q were true, and you're able to buy at P probabilities, you do want to optimize. What you would like to maximize is the logarithm of Q over P. Basically because in Breiman's story, it's because you want to maximize the logarithmic growth rate of your capital in situations where you're making successive bets. And here, that idea is relevant because of the way statistical testing works. Sometimes we do a statistical test, we're not satisfied, and we would like to do some more. Well, if I multiplied my money by so much, and then I do decide to bet some more, I can multiply it by more, so it's multiplicative, and that's why the logarithm is relevant. Yeah.
What is Q of capital Y over P of capital Y?
What is Q?
So, like, we have the likelihood ratio for individual events. What is it for the whole?
Well, this is the likelihood ratio after you see the observation.
Right.
It's what my score actually is. This is the same thing thought of as something that I don't know the value of yet before I see Y.
So it's just another random variable.
It's a random variable, yeah. If you know that language, Y, capital Y is a random variable. And so Q of Y over If we're talking, if the random variable, if it's a continuous distribution, of course, these would be densities, but I didn't want to get into the technicalities. Other questions?
So you have a specific alternative distribution in mind?
Well, yes, I could. But what was the interesting thing was, any time I make a bet that reveals a 1, it's the final of my bet. It seems that I could either start with it in mind, or I could have chosen my bet with some other ideas in mind. But from my bet, there will be an alternative. It will define an alternative distribution. Yeah. But if I did have the alternative distribution in mind, then I would want to choose this betting score instead of some other betting score, R over P. Because if I think Q is right, the logarithm of my wealth will have a bigger expected value when I use this betting score than when I use this betting score. That's what this slide is saying. A little more content. Okay, so let's talk about significant. Now, that's the idea of betting score, the idea of how I would test a hypothesis using betting. And I've related it to the notion of a likelihood ratio. But now let me come back to what at the beginning I said I'm going to give a new interpretation of, I'm going to give a betting interpretation of significance levels and p-values. So let me come back now to the significance level. How does a significance level fit into this? Well, a significance level is where you make a 0-1 bet, or a 0 all or nothing bet. When we say that the significance level is alpha, and usually alpha is 5%, or, that's the standard example. If I bet 5 cents that E will happen, in other words, I get back. Let me pause here. What is the usual definition? The usual definition is alpha is the probability the test rejects P. Let's say alpha is 5%. Then this event, the test rejects P, this test is going to say either we reject or we don't. So that is an event that has probability 5%. Now, the betting interpretation of that 5% is that I can put down 5 cents and I get $1 if the event happens, and I lose my 5 cents if it doesn't. I multiply my money by 20. So that's a little different than the general rule, because my general idea was I could buy any real value payoff. It didn't have to have just two values, 20 or 0. It could have a whole range of values. The only thing I needed was that its expected value was equal to 1. But this is a very special bet here. If I start with $1 instead of alpha, okay, so alpha would get multiplied by, would become 1. So if I started instead with 1, that would get multiplied by, instead of multiplying 5 cents by 20 and getting 1, if I start with 1 multiplied by 20, I get 20. If I spend $1 on my bet, the payoff will either be 0 if the event doesn't happen, or 1 over alpha if it does happen. So this is an all or nothing bet. So in other words, the usual significance testing is a very particular kind of bet. And so I claimed that every bet that I could make defines an alternative hypothesis. What is the alternative hypothesis? Excuse me. What is the alternative hypothesis defined by this? Well, multiply F times P. What's that going to do? It's going to multiply, it's going to give 0 probabilities to everything in E, and it's going to multiply the probability to everything not in E, and the things in E, it's going to multiply their probabilities by 1 over alpha. The people who do significance testing hardly ever believe that alternative hypothesis. That's not a plausible alternative hypothesis. They don't think that alternative hypothesis is basically saying the probability for the rejection region is 0. And you wouldn't, that's not normally what you're thinking. From this point of view, I'm not just interpreting this as in a betting. I'm not just giving a betting interpretation to this kind of significance testing. I'm also kind of saying, from a betting point of view, it's not very optimal. It's an example, but it's probably not the one we would do. Why make an all or nothing bet?
So your critique of this orthodox way is different than the Bayesian?
Yes,
critique?
absolutely. Nothing Bayesian.
Yeah.
Nothing
It's
Bayesian.
another critique.
It's a different critique, but it's also, the result is not so different from what people usually do. And in a sense, it is frequentist. That is to say, it is interpreting the probability distributions as something about the world. They're not about my, the P and the Q
My belief.
are something about the world. They're not about my beliefs. I'm saying that if you say objectively this probability distribution P is right, well, if it's right, I shouldn't be able to make a lot of money against it. So I am testing it as kind of the feeling here is objective. I'm kind of replacing the frequency in business. I'm kind of replacing the frequency rhetoric with betting rhetoric, but I'm still aiming at something objective, not something subjective and Bayesian. So power. What about power? So here is what the slide I already showed. The power is the probability that the alternative rejects P. Now, in practice, of course, a statistician, I should back up. In practice, what should I say? In practice, a statistician doesn't have just one alternative hypothesis. They have many alternatives. So power is a function of the alternative hypothesis. It's not a single number, it's a whole array of numbers. And I should say, I should make some reference to, going back to this, the theory, if you did take a stat course and you studied significance testing, you probably heard about type 1 error and type 2 error. So type 2 error, power is 1 minus the probability of type 2 error. It's related to that. And again, that's a function of the alternative hypothesis. This so-called Neyman-Pearson theory that you are taught in these elementary courses goes back to a famous paper written by Neyman and Pearson, Jerzy Neyman and E.S. Pearson, in the 1920s, and they had something called the Neyman-Pearson lemma, which talked about what is the optimal rejection region to use. How should you choose a 5% region to reject? And their answer was you should choose a region that has the highest likelihood ratio between P and Q. And they did that looking at just one Q. So this idea of looking at just one Q to do your theory, is also standard in that theory. And in fact, that Neyman-Pearson lemma can be thought of as a special case of this argument here about what's optimal given another. But here we say not what is the optimal bet. What is not, instead of the optimal all or nothing bet, we choose the optimal bet that allows you to, that doesn't have to be all or nothing. So in a sense should be more powerful, should be more interesting. So as I said, power is usually ignored in social science. There's two reasons why it's ignored. One reason is because it's hard. Part of the problem is that you have to look at all the alternative hypotheses, and it's hard to calculate. The other reason is that a lot of times people would rather not know. Because the sample size that they can get is so small that they're not going to have very much power, and they'd rather not hear about it. But then, if they do succeed and get a significant result, the problem is that it then becomes obvious to the professional mathematical statistician that they were just lucky. And this is not so obvious to all the people who publish articles with low power. And we've seen recent cases where the very best journals in psychology had a lot of articles of experiments with very low power that got significant results and been published and were very influential. And then there was a group of people that decided to try to replicate them all. And they found out that many of the ones with low power could not be replicated, which is what you would expect. But the literature was ignoring this very elementary point. So, I mean, an example of something with low power, I gave an example here. If you flip a coin 100 times, and you test it being a fair coin, then what are you going to do? You're going to look at the difference between 50. If it's a fair coin, the number of heads should be about 50. And you'll reject it 5% if the number of heads is less than 40 or bigger than 60. But if you just barely reject, if y is equal to 61, that would be, the question is, what is your alternative hypothesis? If your alternative to it being a fair coin is that the probability of heads is 0.52, it's not a very big difference, and getting something so far away from 50 has only a 5% chance if it's a fair coin, but it has only about a 6% chance if it's 0.52. So that's an example of where the probability that it's rejecting under Q is almost as small as the probability of rejecting under P. It has low power. So the right way to test against this alternative, the way I'm recommending, is the likelihood ratio. And if you do the likelihood ratio, this is a binomial example. I use a normal approximation to get this, but this is a binomial example. The likelihood ratio is very easy to calculate. It's 2.2. So you would only, if you did what I'm recommending, you would only multiply your money by 2.2, not by 20. So doubling your money is okay. I bet against it. I doubled my money. It's okay. But it's not so, it's not overwhelming to double your money. And then I come to p-values. That's more complicated. So for some of you, this is new. But this is what is used in all the publications. I'm in a business school, and our accounting and finance faculty do studies about what affects. They do studies about the behavior of business, and every paper reports p-values with no power. Every paper, we're doing our job candidates now. Every paper has got p-values. That is kind of. So, how many of you have studied p-values? Okay, so most of you have. So, you may still find it a little hard to remember. So, when you look at a p-value, how is that defined? And here the distinction between the capital Y and the little y comes into play. Because what we do is we have a test statistic. The use of the word statistic here was also introduced by Fisher, R.A. Fisher, in the 1920s, in a famous paper in 1922. And a statistic is something you can calculate from the data. You don't have to have any hypothesis. You calculate it from the data. So you have some statistic you can calculate from the data, and the probability distribution, since it gives you probabilities for y, it will tell you probabilities for how p comes out. So little y is the value you actually observed. After you observe it, you can calculate the probability that you would observe something that big or bigger. So it's a natural thing to do. And it goes back to the 1820s. I'm just looking at the first table that gave p-values was published, as far as I know, was published by Joseph Fourier. So there's somebody who has some respectability in mathematics. But in a way, if you announce, so then P of little y, if P of little y comes out very small, like 1%, people like to say, well, we can reject the hypothesis because something happened that has probability 1%. The problem is, you didn't say, and if you had bet on that, you would have multiplied your money by 100. The problem is you didn't bet on it. You didn't say in advance that you were going to bet on it being less than 1%. You waited to see, because you wanted to reject even if it came out 5%. But you didn't want to settle for 5%. If it came out less than 5%, if it came out 1% or 1/10 of 1%, you wanted the credit for that too. So you didn't say in advance what your bet was. So you're cheating. You're cheating. If you say that this is something, if you want that 1% to mean that you could have made turned your dollar into $100, no. You could only do that by cheating, by knowing what the result was and then betting on it, pretending you didn't know or something. So how could you fix that? There is a way you could fix it, and that is that one way to fix it is not use p-values. You could test the way I'm suggesting by betting in the first place. But if somebody is telling you the p-value, how should you interpret it? So you could, one way of doing it is to take a function of the p-value that has expected value 1 and make that your bet. So you could do that before you see how the p-value comes out. So my favorite function of the p-value is 2 over the square root of p. When p is less than or equal to 1/16 and 0 otherwise. So this says I'm not going to claim any credit if the p-value is less than 6%. 1/16 about 6%. 6.25%, I won't claim any credit at all. But otherwise, I will take its square root and double it. I like this rule because I can remember it. And I can even do it in my head sometimes. So if your p-value is 1%, the square root of 1% is 10%. So it's 1/10. So this is 10, I get to multiply it by 2 is 20. So if you get a p-value of 1%, I multiply my money by 20. So it turns a 1% level into a 5% level. If that's not good enough for you, well, if you don't like giving up any credit at all when it's less than 6%, you can change this to 25%, but you'd lose the 2. And of course, there's a zillion other rules too. There's no shortage of functions that have expected value 1. But this is one.
That's not the only one, that's your favorite.
That's my favorite.
Yeah.
It's my favorite because it's easy to remember. That's the only reason. It's easy to remember. And I feel like it would be good to have a standard. The point is that it doesn't matter what it is, but if you're not going to cheat, you're going to say in advance what it is. So I can say in advance, from now on, this is how I'm going to interpret p-values. I say it in advance. So that's how I'm betting. I can't.
P-value is a continuous variable. So if we say p-value is 1%, I think the probability that it is indeed 1% is 0.
This probability that where there's an inequality here, right?
Yeah, but p-value itself is a continuous variable, right?
Right. So I take a function of the continuous variable, which has expected value 1, under the probability distribution.
Yeah, I understand.
Yeah.
He's saying that a p-value is itself a random variable, and it's a continuous random variable, which means it has a probability 0 of taking any specific value.
Usually. I mean, it might be discrete. Yeah. Yeah. Are we on the same page?
It depends on y. If y is continuous.
Yeah. P is a function of. So this is a little y and big Y thing. When I wrote this formula, I had a little y here. But now I say, well, let me think about how that'll come out. There can be different values of little y. So I look at the function of big Y before it's known. I take a function of P such that before it's known, the expected value of f of P of Y is 1. And this has that property. I explain why here. I think I've not been clear.
Yeah, so okay, my point is that I cannot bet that I say if it's 1%, then I get 100. I think for me it's unfair because I think if it's the probability for p-value to be 1% is less than 1%.
Right, so the normal idea was that the p-value being 1% means that you would bet that it was going to be 1% or less. And then you multiply your money by 100. But as I say, even that is cheating because... okay, so that's p-values. So this is my main point of my talk. I guess I have another 10 minutes maybe to know these rules. The main point is that we can communicate statistical results better using a language of betting. So what I'm, I guess in fact I am changing a little bit the standard way of doing the statistics, but I'm saying that my main point is that if we talk about it in terms of betting, people will understand that that they won't make these mistakes so the p-value tells you something absolute. We know that I could have been lucky. That's the main point. Now, point 2 goes more to what's in our book, that we can communicate even better if we use fully defined games. So this is the kind of betting game that is studied in our book. For example, if we're tossing a fair coin, what is the betting game? And we're going to do it 100 times in this example. I have 2 players in the betting game. One is the bettor, who we call Skeptic, because he is testing the probabilities. And the other player is reality, who decides what the outcomes are. The Skeptic starts with $1. That's what we're doing in these examples. And in every round, he chooses the stakes of the bet. And this can be positive or negative. If it's positive, he's betting on a 1, which is like heads. If it's negative, he's betting on a 0, which is like tails. So his payoff is going to be, he's going to take his previous capital and add to it his stakes times 1/2 or minus 1/2. 1/2 of its heads, that's 1 minus 1/2. Minus 1/2 of his tails, that's just 0 minus 1/2. So this is just a way of formalizing the betting. Now, that's a protocol, it's not a game. To have a game, what do you mean to have a game in modern game theory? You need to tell who the players are, you need to tell what the rules of play are, and you have to tell who wins. You have to have a rule for who wins. So there's lots of different rules for who wins. Every theorem in probability theory is sort of a different rule for who wins. So for instance, the law of large numbers, the rule for winning is this. Skeptic is going to win if his capital is always positive. This is the point that he's not risking more than that $1 he starts with. He's not allowed to borrow money. He doesn't have any line of credit. He can only risk the $1. So he has to keep his capital always positive, and he's going to win if he multiplies his money by 20, or, I mean, he has to do this, but he also has to do one of 2 things. Either multiply his money by 20, or else reality, or else make sure reality stays within 1/10 his average. What is y bar? The y's are 0s and 1s. So y bar is the frequency of heads, the number of heads divided by 100. So y bar minus 1/2, it has to be within 10 percentage points of 1/2. And Skeptic, this is the central limit theorem, tells us that Skeptic has a winning strategy in this game. So that takes what is a theorem in probability theory and and makes it into a theorem in game theory. So that's the sort of idea of our book. Everything that you did in probability can be everything, almost everything. Most of what standard results in probability theory can be translated, can be given a game-theoretic proof. You don't start with any measure-theoretic assumptions. You just start with the game. How does a probability distribution represent a phenomenon? The usual way of thinking about how a probability distribution represents a phenomenon is that if you pick out a event of small probability, it won't happen. It's a good probability distribution. If you pick out an event of small probability, that's not going to happen. That makes it a good probability distribution. But the game-theoretic, the betting way of saying that is that a protocol represents a phenomenon if an event that allows Skeptic to multiply his capital A risk by a large factor, like this one, will not happen. So it's all this, what I said before, that the interpretation of probability, and Doran invited me to give a philosophical talk, and this is why the talk is philosophical. It's saying the interpretation of probability here is betting. Now, statistics, that's probability. Statistics is more complicated than probability. Why is it more complicated? It's more complicated for two reasons. One reason is that the game, I should go back to this game. This game is did I say perfect information? It's a perfect information game. The players see each other's moves as they are made. But in statistics, we're standing out, the statistician is not in the game. The statistician is not necessarily the skeptic. The statistician is certainly not reality. The statistician is standing outside the game and only sees part of what goes on. Now that corresponds to, I mentioned a paper by R.A. Fisher in 1922. In that paper, he introduced the word statistic, he introduced the word parameter, and he introduced the idea that the theoretical statistician starts with a class of probability distributions. Not a single one, but a class. And he doesn't know which one is the right one. So how does that get translated into the game-theoretic picture? In this classical picture, the statistician doesn't know which probability distribution is right. In our picture, the statistician doesn't see the whole game. He only sees some things from the game. And also, there's a second point, which is that the betting offers may fall short of a probability distribution. There's no reason, if we have this kind of betting picture, there's no reason why the offers that you're testing, the theory that you're testing, it may not give probabilities for everything. That's not always so clear the way statistics is taught. That's not always clear, but it goes on all the time. And there's now a community called Imprecise Probabilities that advertises this point. So let me show you an example of where the betting offers are not a whole probability distribution. So in this example here, the betting offers were a whole probability distribution because if I can bet, this is the probability of 1/2 for heads, and it doesn't change. It's the same on every trial, no matter what happened before. That is the model of independent, identically distributed trials with probability 1/2 every time. Okay, this is different. This game is different. Here, Skeptic is also announcing how much he wants to bet. And reality is announcing a number between -1 and 1. doesn't have to be, you know, in the previous example there were two numbers, 0 or 1. Here it can be any number between -1 and 1. And Skeptic's payoff is that number between -1 and 1 times how much he bet, which can be positive or negative. So he's betting on, we could think of this as a model for errors. So in 1821, Gauss discussed the probabilistic model for errors, and he said the two main assumptions are the errors are bounded. We don't usually do that now. We assume the errors are a normal distribution, which is not bounded. But the tails go down so fast that it's practically bounded. But Gauss said, let's assume it's bounded. And he also said, let's assume that errors of equal but opposite sign are equally likely. Well, this is a way of getting those ideas, incorporating those ideas without giving probabilities for the error. There's no probability distribution given for the error. The only point is that I can buy the error for 0. I can buy the error for 0. I don't have to pay anything. I just say, how much of the error do I want? I want this much of it. Okay, that'll be my payoff. Could be positive, could be negative. If I want to, I can also reverse the sign. I say, I want minus the error. Okay, how much of it? And then equals -10. Minus 10 times the error. So the idea there is like the error is expected value, its price is 0. But on the other hand, we don't get probabilities for it. So that just sort of says, you know, the positive or negative errors are equally likely. But we say that without giving a probability distribution for everything. Now, we can do, this is enough to do error theory. The next, how much?
Minus 2 minutes left.
Minus 2 minutes.
Yeah.
I have 2 minutes.
Very, very interesting. Yeah.
So, if we look at this game and put in a rule of winning, the skeptic can win if he keeps his capital positive and either multiplies it by 20, or else the average error is less than 0.27. He can win that game. Now, if this were, why is it 0.2? Back here, it was 0.1. But that range was only, I had a range, there was only a unit length. Well, and here, actually, in fact, this is only, the distance, this is, the absolute value of this is always 1/2. Here, I've got a bigger range. The range is doubled from -1 to 1, so it's natural that this number would be doubled. But the fact that I don't have a full probability distribution means that I sacrifice a little more too. But it's not so bad, not that bad. This is from Hoeffding's inequality. In our book, we have the game-theoretic form of Hoeffding's inequality, and that gives this result. So the statistician can use this if we make, here's the game where the statistician stands outside the game and doesn't see the whole game. So what I've added here is that reality announces a number alpha. And then the statistician does not see that number alpha. He only sees the measurements of alpha with these errors. So he only sees the measurements. The slide needs fixed. So anyway, he only sees part of it. And we can do statistics with this